Hello, this is Professor Bailey at Dallas College for Elementary Statistics using ALEKS. Specifically today, we're lecturing on Chapter 2.2, Frequency Distributions and their Graphs from Essential Statistics. As I've done in the past, I've just let you read these. These are objectives for today's lecture, and I'll move forward. Frequency distributions for quantitative data. Just like we saw in the last lecture where we were building bar graphs for qualitative data, where each of the bars represented a specific category, we're going to do something similar for quantitative data. But remember now we're quantitative data is numerical in nature, so there's not necessarily a specific class that represents all the numbers. Yes, all the numbers do fall in a category, but now we're more focused on the level of numbers or the numbers that are reported, not everyone says I'm a smoker. We're looking for some other numerical data, and that's where we do this. We divide these responses into classes, and this is just a group or a range of values based upon our lowest and highest number of data points collected. So classes are, by definition, they're intervals of equal length. In the table that you see on the bottom, you'll see that the first class goes from 0 to 4, the second class from 5 to 9, etc. And so what we're doing is we're recording all the responses that fell in this range of 0 to 4. So 2 of the responses fell in that first class range. Okay, it's important that you build classes that are intervals of equal width, or it could potentially skew some of your data and your observations. The lower class limit of a class is the smallest value, or the values that we see on the left in each row. So we have 0, 5, 10, 15. These are the lower class limits, because like for the first class, it goes from the lowest value of 0, the lower class limit, to the highest value of 4, which is the upper class limit. Okay? You can always calculate the size of a class by subtracting the next class's lower limit from the previous, or 5 minus 0, or 10 minus 5, or 15 minus 10, and you can see that all of those are equal, and they should be equal. If you do that and they're not equal, you've got to rebuild your tool here to calculate your data. So when we're constructing a frequency distribution, we're first going to choose a class width. What are we going to do? We're going to look at the lowest observed value in this category. We're going to look at the highest value, figure out, what is the range between those, and make some decisions about the values, how wide each class should be. If our values go from, let's say, 1 to 5,000, our ranges are probably going to be pretty big, like maybe 0 to 1,000, 1,001 to 2,000, etc. Also remember that you don't want any overlap. You don't have a class range that goes from 1 to 4 and from 4 to 8. Often you'll see things like 1 to 3.99 and then 4 to 6.99, etc. So the first thing we do is choose a class width by looking at all our data points, finding the lowest value and the highest value, and then making a call for how many classes we want, and then dividing it into equal widths. Once we've done that, we can choose the lower class limit, again, making sure that we start below the lowest data point that we have, or at that lowest data point. Then we compute the lower limit for the second class by adding the class width and create all the classes. And we can create all the class limits that way. And then of course we stop when the largest data value is included in a class. Once we have all of our tables set up with our class ranges, the range of answers that we're looking for, we just count them. How many are between 0 and 4? How many are between 5 and 9, etc., or 5 and 10? Okay? and then we fill in the table. Let's go through an example step by step. Here we have the emissions in this table. So there's 65 entries into this table of the unit of grams of particles per gallon of fuel in their emissions. And so we want to do a distribution, a frequency distribution using a class of 1. Okay. So the first thing we're going to do is look for the lowest values and the highest values so we can figure out where to start and where to finish. I can see that we have values that are less than 0, or excuse me, less than 1, not less than 0, of course. I see a 0.25. So we're going to start the first class at 0. The largest value, I see a 6 or 5.94. I see a 6.55, so it's likely that we're going to want to go to 7. And remember, we're going, we want a class width of 1. So if we start at 0, remember the next class has to start at 1, so that 1 minus 0 equals 1. So our first class is going to go from 0 to 0.99. Again, since the smallest value in the data set we just mentioned was 0.25, we choose 0 as the lower limit. Since the classes are constructed using a class of 1, then our upper limit for that first class is going to be 0.9, 1 to 1.99. We keep going through until we get all the way to above 6.54, the highest value. Okay. At this point, we would just go through, and so, for example, 1.5 would be in the second class, 0.87 in the first, 1.12 in the second. We just actually, a lot of times we make slash marks, or we just basically count them, making sure that when we get all the frequencies, they add up to 65 in this study. Here we've entered all the observations. There were 9 in the first class. If you go through these and count, you'll see them. There were 26 between 1 and 1.99, all the way down the table. And so we've created the frequency distribution for our study. Now, if we want the relative frequency distribution, remember what we do is that we then take that number of observations and divide it by all of the frequencies, the sum of all the frequencies. In this case, we had 65 data points, and we calculate that. Remember, the relative frequency can also be thought of as a percentage. So roughly 14% were in the first class, 40 in the second, looks like 46 in the fifth class, etc. So this is going to give us some information about the level of emissions in the vehicles we tested. And again, if we move this into a bar graph, then we can kind of get the data much more effective visually for most. Okay, so we use something called a histogram, which is a specific type of bar graph for quantitative data. Okay, it's basically the same as we did before, and there's some interesting rules, and I don't know the background for the rules, but it's basically a bar graph which uses the class width. It's one of the reasons why we keep the class width the same, because so that all the bars are going to also be equally the same. And so the area of each bar, to some degree, also relatives the proportionality of the responses. Okay. Histogram specifically, one of the rules of histograms is that the bars touch, that the bars are close to each other. There's no spaces between bars. And I'm not really sure what the logic is there. Perhaps it's again the idea that you go from 0.99 and then you start the next class at 1, so that all data is accounted for, and maybe there's some kind of subconscious message that if the bars are separated, maybe there's data in between. Okay. The frequency histogram and relative frequency histogram you can see below. And just like the other bar graphs that we saw for the qualitative data, they're roughly the same shape, because if the largest number of responses is in a category, then the percent of the responses is going to be largest for that same category. The difference, of course, in both of these is the scale on the vertical axis. On the left, we see the on the left, we see the actual counts or the frequency, and in the graph on the right, we see the relative frequency. So on the left, it's the number of times, or a number, in this case, the number of vehicles that had the particulate emissions at a specific level. Oh, and then on the graph on the right, it's a decimal, again, that corresponds roughly to, not roughly, to the percent of responses in that specific category. So figuring out how many classes to have is, I don't know if it's a science or if it's an art, probably comes more with experience, but the number of classes can affect the shape of the histogram. And sometimes you draw something and you realize it's too far out. Sometimes you might want to make less classes, etc. Too few classes can produce a histogram lacking in detail. Too many classes can produce a histogram with too much detail. So on the left, we see a lot of classes, and on the right, we see fewer classes, wider class length. So on the left, you can see, remember, each of these bars is a class width. So it looks like we have maybe each width is like 0.1. Where on the right, each class is width of 2. And so here, when we have too many classes, it's hard to pinpoint the data. When we have too few classes, it's also hard to pinpoint the data. So you can use technology to build these graphs. Here you have Excel. You also see the TI-84 Plus, which is listed in our required calculators for this course, or the calculator you can use. So I'm not going to spend a lot of time on the technology. Every section that we're doing some calculations, you are certainly privy to using technology to find graphs, to find information. To me, this course is very much contextual. No one calculates any of these measures by hand. We use tools to do that, and so you certainly can use the tools in this class. Your textbook has a using technology section at the end of every section, 1.1, 1.2, that uses technology in the content for that section. These are highly detailed instructions with examples, and in ALEKS you'll have some help there to find them as well. I highly recommend them, and in my course I'm really signing pretty much all the Excel practice problems. And the reason I'm doing that is because Excel is used widely in industry, not only for statistics, but for all things. And so it's just another competency that I want you to have when you go into the business, when you go to work. It also can be used for a variety of things in your own life, like budgeting, scheduling, etc. It's sometimes necessary for the first class to have no lower limit or no upper limit. Okay? What does that mean? It's like we don't know exactly where to stop, and there may be some kind of logical place where to stop. Age is a really great one for that. You know, you might get to a point where you don't care about upper ranges or lower ranges. So you might say 5 and under, or you might say 70 and above. Um, when a frequency distribution contains an open-ended class, a histogram cannot be drawn. And so that's one drawback from having an open-ended class. It can't be drawn because you don't have, without excluding that open-ended class, you can't draw it for that class because it doesn't have the same class width. Honestly, but I've seen histograms drawn for these excluding that data, which I'm not sure how relative that is, especially like in this case, you see that there's a lot of data. This was the number of deaths, I'm not sure for what, but you can see that that would be a huge amount. The largest percentage would be from that category. But again, you can't use a histogram because histograms are also about relative area. And so because there's no equivalent width, class width, the area is skewed as well. This was the frequency distribution of the number of deaths in the US due to pneumonia. And you can see that the upper class is the open-ended one. When data is discrete, we can construct a frequency distribution in which each possible value of the variable forms a class. And remember, discrete is finite. So here, like the question was how many children they have. So each response gets its own class or own frequency or own bar, if you will. The other thing that we're concerned about in statistics, and we're going to be focused on this a lot, is the shape of the data set and whether it's skewed. And so the visual representation is the shape of the data. And we use skewed if it kind of goes downhill to one side or the other. I like to think of it more as a tail. This kind of visually helps me, like an alligator tail, and it helps me with the vocabulary itself. So if the tail is going down to the right, we call this skewed to the right or positively skewed. The tail, as we are going up in values, the tail, the number of frequency is going down. If the tail is off to the left toward the negative direction, we say it's skewed to the left. Again, I'm thinking this looks like the alligator's tail, and it's pretty easy to remember. Skewed left is to the left, skewed right is the tail is to the right. We also sometimes say right-tailed and left-tailed. Symmetric histograms is if it looks like a almost like a bell curve, we sometimes say, where the right half is a mirror of the left half. And you can see in this diagram that's on the page, it's not perfect, but it's got a roughly bell shape or symmetric shape. And we're really looking for that in a lot of the higher level statistics that we're even going to do in this course. We also have something called a uniform distributed histogram, or a uniformly distributed shape, I should say. And that's when roughly almost you have the same value, the same frequency of responses in almost every case. So you're looking at a chart that's roughly level or flat, plane, like a plane. And so we call this uniformly distributed. It's also possible that there's more than one peak. If there's only one peak, it's called unimodal. If there's two peaks, if there's two clear, distinct peaks, not like this little peak here on the, it's a lower peak, but it goes down and then back up. We don't call this bimodal. It's only if there are two distinct peaks that look like two mountains side by side, then it's bimodal. Again, here we have some, whoops, looks like I'm sliding into the information already. I'm not sure how I did that. Sorry about that. But these are pretty straightforward. I think there's another slide coming up. Only this is our final slide. This is all the stuff that we covered here. And hit pause if you want to go back and check your notes. There's a few things to learn in here, but again, we haven't gone really deep into anything that's rocket science yet. but good science we're still at. So make sure you get this down in your notes, and we'll see what